Good afternoon, ladies and gentlemen. I'm Takata from Thermophysical Properties Division. Today, I'm very pleased to have a very distinguished professor from Germany, Professor Peter Stephan. So first, I would like to briefly introduce him. Professor Peter Stephan graduated from Technische Universität Munich, TU München in 1988, and after that he received a PhD from University of Stuttgart in 1992. After that, he became a research assistant and Marie Curie Fellow at the Joint Research Center of the European Commission of Ispra, Italy. Then, from 1992, he worked for the as a R&D manager and senior process engineer at Daimler-Benz Group. In 1997, so he became a full professor for technical thermodynamics of Technische Universität Darmstadt, and also the director of the Institute of Technical Thermodynamics. And from 2007 to 2009, he served as the dean of the mechanical engineering faculty. And also from 2011, he served as a senator of the TU Darmstadt. So his main research field is phase change, especially in boiling and evaporation and condensation. And he received many awards, and I'll pick up a few among many awards. So in 1995, he received the Sadi Carnot Award for thermodynamics from International Institute of Refrigeration. And 2008, he received 2 awards from ASME, American Society of Mechanical Engineering. So one is I²CNER 08 Outstanding Researcher Award, and the other one is a Journal of Heat Transfer Outstanding Review Award. And so last year, he received the Nukiyama Memorial Award from Heat Transfer Society of Japan. This award is very variable and very, how do you say, it's a big award in our society. So today's his talk is local heat transfer near moving 3-phase contact lines and its influence on nucleate boiling and drop evaporation. So I'd like to invite him. Please do start.
Thank you very much, Yas. Thank you very much for this kind invitation, Professor Takata Sensei. And thank you very much for inviting me to speak here at I²CNER. I saw a very nice building, and I can congratulate you to this beautiful site here, and I'm happy to be here. I'm also happy to be here in Japan during the last 2 weeks of the next 2 weeks, which is a fellowship of the Japanese Society for the Promotion of Science, JSPS. Thank you very much. Before I talk about the subject that you can read here and that you just introduced, I would like to briefly introduce my university and my institute so that you know where I'm coming from. And then I go into science. First of all, this is one of the oldest buildings in Technical University for mechanical engineering. Our university was founded in 1877. So it's a not very old university, but in Germany, a rather old university. And for those, and typically outside Germany, nobody knows where Darmstadt is, but everybody knows where Frankfurt is and where Frankfurt Airport is. And We are very close to Frankfurt. We are even a bit closer to Frankfurt Airport than Frankfurt itself. And Frankfurt has no technical university, even though it's a very big city. Darmstadt is a smaller city, only 150,000 inhabitants, but it's very close to Frankfurt, and it's the major technical university in this area of Germany. We have in total about 25,000 students, a little bit less than 300 professors, and something about 2,300 research assistants, and also technical and administrative staff. We are divided into 13 departments. 50%, almost exactly 50% of these departments are engineering departments. I belong to the mechanical engineering department. That's why I put it in red color here. And there's electrical engineering, civil engineering, and so on. About 30% is natural sciences, like physics, material science, and 20% is humanities. But these humanities are always all are directed into technical issues. So humanity science in a technical environment, let's say. We have additionally, just since 2 years, subdivided the university into 5 interdisciplinary research clusters in different fields, so like production engineering, material science, and also one of these interdisciplinary research clusters is thermofluidics and combustion engineering. I have the pleasure to be the speaker of this research cluster in our university, and this tries to cross in research the borders between the different departments, which is sometimes easier to do it in a separate research center than in a classical department. We have one national research cluster of excellence. There was a big excellence initiative of the German government some years ago, and we were able to win one of these research clusters, which is the cluster or center of smart interfaces, and I have the pleasure to be the co-director. I will show you what we are doing there. And we have 2 national graduate schools of excellence. Rather recently, we were successful with our proposal for an engineering science, energy science and engineering school, which deals with many aspects of engineering from different disciplines, but mainly is for master and PhD education. Of course, also for research, but this is a little bit different in a research cluster of excellence. So the main aim is research, and then comes education, and in a graduate school, education comes first, followed by research. This is the mechanical engineering department, 27 professors and institutes, about 2,800 students in mechanical engineering, undergraduate and so bachelor and master level, and about 600 research assistants. We are typically, and every year there's a ranking of national universities and also of specific departments like mechanical engineering departments, and we are typically always among the first 3. Sometimes we are number 2, sometimes number 3, sometimes number 1, but we belong always to the first 3, like, for example, RWTH Aachen and Karlsruhe, for example. Our mechanical engineering department covers basically all aspects of mechanical engineering, like production engineering, thermal engineering, automotive, aerospace, system engineering, and material design. You saw here many logos, and this is the logo of Technical Thermodynamics, and this here is then the Institute of Technical Thermodynamics, which I'm heading. We subdivided this institute into 3 research groups. I'm dealing basically with a group and supervising the PhD students in the group of evaporation and drying also. My co-worker Tatjana Gambayan-Reisman is taking care for films and drops. All is heat transfer related, of course, and Frank Dammel is taking care for single-phase convection, basically. And since 2 or 3 years, we are more active also in thermal system analysis, which is a quite interesting subject, also in relation with the Graduate School of Energy Technology. And we use, as a kind of cross-disciplinary, different methods like numerical, analytical, and experimental. And together in these 3 groups, we are about 18, at the moment, I think exactly 18 PhD students. We try to do the following, and I will show this later when I come to the details of my scientific presentation. If we do a fundamental research work, we try as often as possible, it's not always possible, but as often as possible to do a generic experiment. This here shows our boiling experiment, for example, together and joined and overlapped and very detailed, related, taking the same boundary conditions and so on for numerical and theoretical studies as for the experiments. And if we gain some knowledge, then we try to transfer this to applications. So let's say 75% of our work at the Institute is fundamental, but 25% we try to push towards applications. For example, we developed a quite nice, in such a generic experiment, we found out that we can have a porous structure where we have evaporation of methanol from this porous structure with very high heat flux, and we implemented this to cool a PC. We took out the standard cooling of a PC. We placed our own cooling with a capillary-driven system, and this works fine, and this is a kind of industrial demonstrator. And we always try to find some correlations here to put them into handbooks, preferably, because I'm the editor-in-chief, into the VDI Heat Atlas, and also we try to develop software. We did this, for example, rather successful here. This here shows an example also of our institute. When I worked in industry and when I came to a university, one of our subjects was also drying of polymers, water-based polymers, basically paints of automotive industry. So we developed with generic experiments a numerical model, very, let's say, accurate models how to dry a paint with using convective dryers plus infrared dryers. And then we wrote a software which is used as a subroutine in a commercial software, and now car industry is using our software to dry artificially car bodies before they are even manufactured. This is our teaching program. I teach basically these courses here up to advanced heat transfer. Advanced heat transfer is condensation and boiling, basically boiling, and these are the undergraduate, the bachelor courses and the master courses. I teach also project management, and my co-workers at the Institute, Tatjana Gambayan-Reusmann and Frank Dammel, teach these things here, which is quite interesting. Sometimes outside Germany, technical thermodynamics is a course not only for mechanical engineering, but also for mechatronics and so on. So the number of students in this course is at the moment 1,200. In 2 weeks from now, we have examinations. That's a quite heavy load, 1,200 students in one class, but it works. Now, this is the Center of Smart Interface, our new building that was just finished last year, and I moved in with my institute last year. This was founded in 2007 within the German Excellence Initiative, and it's an interdisciplinary research center with these different type of disciplines. And meanwhile, since 2007, we hired also six new professors working in this field, and together these 6 new professors have about 100 employees sitting in this building here, together with my institute also here in this institute now. What is a smart interface? We define a smart interface as follows. We say it refers to a fluid-solid boundary interface, so whenever there's a fluid, either single phase or multiple phase, this interface, these interfaces have been designed or built for achieving a specific purpose, namely enhancement or controllability of mass, momentum, and heat transfer. And typically we have only 5 possibilities to influence such an interface, to make a normal interface, let's say a smart interface, and this is by changing, for example, the nano or microgeometry, making small grooves or specific roughness morphology, to change wetting characteristics, that's behind physical chemistry, to apply, for example, an electrical field as an external body force, to have, for example, a porous structure, to have wall fluxes, or to have, for example, a vibration of the surface to enhance heat transfer, for example, so relative motion at the interface. We have subdivided this center in 5 research areas. Heat and mass transfer enhancement, and others like static and dynamic readability, near wall reactive flows, near-wall interfacial flow and transport, and also flow manipulation and control. And we try to do fundamental research and application-oriented research in such a circle. Sometimes we start here with fundamentals and hopefully come to applications. Sometimes we start with applications and go to fundamentals, and sometimes we start from any point. So this is where I'm coming from, university, institute, and the Center of Smart Interface. Now this is my scientific talk. I will first try to motivate it a little bit. Then I will talk about the research method and hypothesis. And then I will present some combined generic experiments and numerical simulations. As I showed you before, I always try to do both at the same time. Generic experiment to study fundamental phenomena, and at the same time numerical work. And this I try to interlink somehow, so to combine. And I will present you two research fields. That's a single drop impingement onto a heated surface, and a single bubble growth, so boiling and detachment on a heated substrate. And they have both something in common, namely the wetting characteristics close of the fluid, two-phase fluid close to the wall. And I will show you what that means for our research. And of course, I will give some conclusions and an outlook at the end. Now, these here are the two points of interest. So we study drop impingement. So a drop comes with a certain velocity onto a hot wall. This hot wall is, in our case, typically above the saturation temperature of the fluid. And this here is a pure vapor atmosphere in our studies mainly. So we have evaporation here, and of course convect. But the drop is strongly subcooled when it hits the wall. So we have convection, convective heat transfer, and evaporation when it hits the wall. And here just more or less the opposite. We have a heated wall and a subcooled or saturated, both is possible, liquid. So at a cavity, there's a nucleation of a single bubble or multiple bubbles, and this bubble is growing and finally detaching due to buoyancy forces and rising in the fluid. Now, why do we do that? We are not so much interested from an application point of view to a single drop impingement, but we try to go in the next steps towards spray cooling, because spray cooling is one of the most efficient surface cooling mechanisms in many applications. We have also more applied projects together with the steel industry, for example, for steel quenching, which is the water spray on hot steel plates. This year, with refrigerants, spray cooling can be applied to chip cooling. And also, automotive industry is quite interested in spray cooling, not really for cooling purposes, but they want to know exactly, for example, if you have a direct injection engine, what happens with the fuel spray when it hits, for example, a valve or the piston, which is rather hot, and you have partly evaporation of the fuel like that. Here I plotted the heat transfer coefficients on a logarithmic scale for different cooling methods. That's basically natural convection with a not so good heat transfer coefficient. This here is forced convection, much better. Then we have heat transfer including evaporation, and then jet cooling, and then spray cooling, even higher heat transfer coefficients. Spray cooling with water due to the high latent heat of vaporization is best, of course, but you can't use water, for example, for chip cooling, so you have to use refrigerants, which are electrically not conducting, and this is typically half an order of magnitude lower. And we try also to use smart interfaces, and with these smart interfaces we try to push the heat transfer coefficient to even higher heat transfer coefficient than with standard interfaces, solid fluid interfaces. And of course, a drop impingement event is the most generic phenomena within a spray to start your research. For boiling, we are looking to single bubbles basically at the moment, but also in some experiments, multiple bubbles, bubble growth and detachment. And as you know, pool boiling and flow boiling is one of the most effective heat transfer mechanisms in many, many applications since many, many, many years, basically in power plants and refrigeration, but also meanwhile in electronic cooling. And if we study a single bubble growth and detachment, This is representative, at least for the single bubble regime in the Nukiyama curve, in the famous Nukiyama curve. But also when you have multiple bubbles that interact somehow with each other, we try to learn from the single bubble, and then maybe 2 or 3 bubbles. We try to learn more about the multiple bubble regimes, and also we try to learn to slowly but certainly go towards critical heat flux with our investigations. Now, the state of the art in both areas from a very general point of view is the following, that the prediction methods for engineering purposes to calculate the heat transfer coefficients are based typically on empirical, sometimes semi-empirical correlations, which have a reasonably good accuracy only for certain fluids in a certain range of parameters. But if you come with a new fluid, for example, or a new range of parameters, from the process, these empirical correlations might be accurate only up to 50% within 50% error. The reason is why these correlations typically are not based on the physical phenomena, but they are really empirical correlations from experiments. Without going into the details of the local transport phenomena, so the dominant heat and mass transfer phenomena and the interactions of these different phenomena are still not sufficiently understood in both in drop impingement cooling as well as in boiling heat transfer. Now the hypothesis is the following, that when you have a droplet impinging on a hot wall that is superheated against saturation temperature, and when you have here a superheated wall where you have boiling heat transfer, that here you have a wetting area where the 3-phase contact line appears. That means a contact line between vapor, liquid, and the solid. And in this 3-phase contact line, there are many studies about these phenomena in this 3-phase contact line. We started to study this in the early 90s, but there are works, much older works by, for example, from Peter Weiner in the United States, who studied and showed there's a kind of, at least in a pure vapor atmosphere for perfectly wetting fluid, there's a kind of adsorbed film, and then you have a region of high heat transfer with high evaporation rate, and then a region with low heat transfer and lower evaporation rate. And of course, this situation is very similar in both cases, drop impingement and boiling heat transfer. That's why we applied also our numerical model for both situations, and that's why we investigate these two different situations with a very similar experimental setup. So the research method is the following. We try again to combine experimental and numerical studies to derive a very basic comprehensive understanding of the very local heat and mass transfer phenomena, and at the end then to develop prediction tools. And we do this from an experimental point of view using high temporal and spatial resolution and a rather broad variety of parameters. So we change fluid pressure, temperature, wall material. We also change gravity by going into parabolic flights, and also in future also onto the ISS, the International Space Station. And we do CFD simulations embedding in multiple scales, so the scale here of the contact line and the largest macroscopic scale outside this contact line, and this is somehow combined. The basic concept of an experiment in these two situations looks like the following, and I start with the boiling experiment. So we have a boiling test cell. The test cell is first evacuated and then filled with the fluid. The fluid is boiled. Typically the fluid is also carefully degassed before we fill it into the test cell. And the test cell is pressure controlled, and we have pure vapor atmosphere above the liquid, the pool of liquid in this test cell. And then we observe the nucleate boiling process with two cameras. We have a high-speed black and white camera from the side with a backlight illumination with a rather high resolution shown here. And we have a second camera, a high-speed infrared camera, also with a rather high resolution. And this, as I will show you in a minute, this camera is able to look through the heater because it's a transparent heater to measure the temperature here at the solid fluid interface. I will show you how this heater looks like in a minute. First of all, this here shows as an example our test setup in our lab, in our university. So this here is the boiling test cell. You have the different windows for observation, the high-speed infrared, black and white infrared camera with a microscopic lens and the high-speed infrared camera. And this here can be set and very nicely controlled by means of pressure and temperature. So we also can control very nicely our heat losses. And this here is basically a similar experiment, but in a parabolic flight configuration. You see me here standing in front of the parabolic flight experiment. So we go with that from France, from Bordeaux, with the help of the European Space Agency, into a parabolic flight situation where we can have gravitational forces as low as almost zero, as in space, and in the recovery phase of the airplane and in the initial phase when the airplane lifts, we have 2G. So here we have, of course, this 9.81 G of Earth, and here we can vary the gravitational forces. And this is typically the fluids that we use in this process parameter range. Now this here is a very similar experiment for the drop impingement. We take the same black and white camera and the same infrared camera, but we change our test cell. Now the test cell has a very similar heater, but here's a vapor atmosphere, slightly subcooled to avoid condensation here somewhere, but this wall is superheated compared to saturation, and then we have a droplet generator, and we can generate droplets that impinge on the wall, and then we observe the impingement process of the droplet at the wall. The heater, in the past, we started with very thin metallic foil heaters, but this had quite some disadvantages. So since about 2.5 years, 3 years, we found a new heater concept. We use an infrared transparent calcium fluoride glass with a thickness of about 2 millimeter. Only for our boiling experiment, we use an ion beam milling technique to just shoot a short pulse and thereby produce an artificial cavity for our boiling. This cavity typically has a size of 20 by 20 micrometer. Then we sputter here on top of this glass, with the help of our colleagues from material science, a 400 nanometer thick chromium-based layer which has some carbon particles inside. This gives us basically emissivity equal to 0. When we observe with the infrared camera in this wavelength range, the infrared glass is fully transparent, and then this has emissivity 1, so we see this temperature. And then we cover that again with a 400 nanometer pure chromium layer, and this is basically our heater. We can contact it with some electrodes here and there, and thereby, due to Joule heating, produce heat here in this layer. The nice thing of this layer is that it has very nice thermal characteristics. If I calculate the thermal capacity per square meter surface area of this heater here, it's very close to stainless steel. And if I calculate the thermal diffusivity of this setup here, it's also even closer to that of stainless steel. So what I basically have with this configuration is a heater that behaves like stainless steel, but it's infrared transparent. And this is something very nice. I always wanted to have a transparent metallic heater, and this is something very similar, it behaves like a metallic heater, but it's transparent. Now this is what we see. We see with our infrared camera of course, an intensity distribution, but we carefully calibrate before the experiment and after experiment. So with our calibration curve, this gives us a temperature, and from this temperature signal, which is the signal then observed from the infrared camera exactly in this layer here, but this layer is basically only 400 nanometer far away from the fluid. So we see this here, and then we want to know the heat flux distribution, and we do this as follows. We take a transient 3D conduction numerical simulation in the substrate. So we discretize our heater, our entire heater. We have low pressure around the heater here, so we have almost adiabatic conditions around the heater here. We know the temperature profile in space, x and y, and in time, tau here, and we use this as a boundary condition, and from that we can then calculate the heat flux profile. So this is the measurement data, and with a numerical procedure we get out of the temperature distribution, we get the heat flux distribution. This is then how it looks like for the pool boiling experiment. So on the left side you see the image from the high-speed black and white camera here in slow motion. That's very slow motion. Typically the departure event takes 2 milliseconds, so it's in slow motion. This is what we see with a black and white camera. We can measure bubble departure diameter, frequency, volume, trajectory. We can also, with using a micro-thermocouple, you see the tip here, we can measure the temperature in the two-phase boundary layer, either in liquid or vapor phase, depending where the tip here of the thermocouple is. We see with the infrared camera the temperature profile, and we see the fluctuation of the heat flux profile. You already see here that you have a ring-shaped cold area, because here, when the bubble is growing, there's a ring-shaped contact line, and there's a strong evaporation, high heat flux, and high heat flux means strong cooling, so low temperature, strong cooling, strong evaporation near the contact line, near the moving contact line. It's moving in 2 directions. This here now is the drop impingement experiment. I start the movie soon, so you have here the black and white camera image, the infrared camera image calibrated into degrees Celsius, and then the reconstructed by numerical calculation heat flux profile. You see here 2 curves plotted versus time. This here is from here to there, it's 100 milliseconds from here to there. You see that the droplet will come. You see that the mean temperature is plotted. The mean temperature is average temperature over this entire surface area of this field of view. And the mean heat flux is the mean heat flux averaged over the entire field of view. I start the movie. You see that it's still heating up, so that means it's not in fully steady state conditions due to the Joule heating, but it's only 0.2 Kelvin. Now the droplet comes. It hits here, the wall. There's a sharp decrease of the mean temperature, and even more sharp at the contact line region, and the sharp increase of the heat flux. So the droplet is cooling the wall, temperature goes down, mean temperature goes down, and local even more, and the heat flux goes up. So it's a very good cooling. This here is the cooling rate of natural convection, very low, and then the cooling rate goes strongly up when the droplet impinges. I start this movie maybe once more, and then have a look here when the droplet comes and hits the wall, how it cools the wall in the mean values in the field of view, and you can see the ring-shaped strong cooling near the contact line. Here you see it. And you also see here that the droplet first spreads, because you have high inertia forces when it hits the wall, depending on the initial velocity, and then surface tension becomes dominate. Then it moves into a droplet shape like this, depending on the static contact angle, and then it sits. It's a sessile droplet at the end on the wall, which partly evaporates and will disappear then with time due to evaporation. The numerical modeling approach is the following. So it's rather complicated, and we take our specific 3-phase contact line model, which was developed in the past, started first in the mid of the 90s or early 90s for evaporation near the contact line in heat pipes, and then it was applied to boiling situations, and then meanwhile also to droplet evaporations. And we have this model further developed a little bit, and then we include this model as part of a larger macroscopic model. And this macroscopic model is based on a volume of fluid solver. We typically use, meanwhile for this very fundamental studies, only open foam. And in this open foam code, using the volume of fluid solver, we have implemented our specific, I call it homemade models and codes. Basically, we have implemented the following into OpenFOAM. We have implemented our own interfacial phase change model, so for evaporation, based on the temperature gradient at the interface. we have implemented a level set method and a 3D interface reconstruction in each cell. This is very important because due to these high curvatures, you have to know very accurately to track your interface. Typically, volume of fluid smears out the interface, and we have to know very exactly the position and the shape of and the curvature of the interface. That's very important. And this typically does not work with standard methods. That's why we developed our own 3D interface reconstruction in each cell and combined it with the level set method. And we use the subscript scale model for contact line description. Either in the past, typically we used this in an interactive way. Meanwhile, we do pre-calculations with the contact line model, store this data in a lookup table, and take then the data from the lookup table during the macroscopic computations, because it's from a computational time point of view, it's much faster. And then we have a piezo loop, and then we go to the next time step. And of course, we solve also the transient energy conduction equation in the solid, and this is all combined then together in a single code. You will see some results even in this next slide. So here, when I start the movie, you will see a droplet impinging on an initially heated wall, hot wall. So the droplet, when I start it, it comes with a certain velocity when it impinges the wall, and then it will spread over the wall. Then it will, due to surface tension, settle down on the wall, and in between you see the cooling of the wall. So you see the isotherms in the wall, and of course the wall temperature here is below Leidenfrost temperature, so it is able to wet the wall. Here you see now what happens, how the wall is cooled and the droplet impinges, and you see that this here you have a rather cold area in the middle, in the beginning, and then a very cold area here near the contact line. So of course, when the droplet impinges in the first moment, it cools very strong in the center due to convective effects, and then evaporation starts, and then it cools stronger here close to the contact line. So this is the numerical simulation, and then we take our experimental data and the numerical data and we compare. And the good thing is that we do all in our lab, so we exactly know the boundary conditions from the experiment, and we can really match it, and you see it looks rather nicely. We don't calculate here the falling of the droplet. We start the droplet just with an initial velocity just before it hits the wall, because we want to save computational time. Because such a droplet impingement event by means of numerics, we have a rather high-speed computer, takes almost 2 days for this computation. So it takes rather long computational time. But of course here you see some fluctuations of heat flux, because it's never in the experiment perfect as here in the two-dimensional rotational symmetric simulation, but it looks very close, and also the details here are quite nicely reproduced by the numerical simulations. Now, from the numerical simulations, we can go into much more detail of the transport phenomena than we can in the experiment, because in the numerical simulation, we see exactly where does the heat go to. So I start here again a small animation where the droplet is sitting here, but I show only part of it from the center line, and I show where the wall is hot, where this energy of the wall goes to. And we see when the droplet, this is the total heat removed from the wall, and we see when the droplet spreads, it goes basically into sensible heat and heats up the droplet. So the droplet temperature is rising. But then when the droplet, the surface tension forces is dominant and the droplet recedes in this direction, then the phase change starts. I start this movie again. And this here is sensible heat to the vapor, so directly from the wall due to natural convection to the vapor. So this is very little amount of heat. And if you add these two, this gives the total heat removed from the wall. So you see, first it's more sensible heat, and then it's more phase change heat. Why? We can see this also here if we plot, and here we compare again experimental data with the uncertainty of the experiment and the numerical data. We see that we have basically three phases of the droplet impingement event. First of all, plotted the radial position of the contact line versus time. the droplet hits. When it hits, the contact line radius is 0, and then the droplet spreads. So you have an increase of the radial position of the contact line up to the maximum here for this droplet of about 1.5 millimeter radius. And then this is inertia force dominated. Then the surface tension force are dominating. Then it recedes again. And then you have a small, let's call it vibration until it reaches not steady state because it's still evaporating, but until it reaches the sessile droplet situation. And now what we can't see in detail, of course, from our experiment, we can see the overall heat transfer from the wall to the fluid that we can measure, but we can't see the details. Where does the heat go to? Does it go into the contact line evaporation? Does it go into the evaporation in the center of the droplet? And we see the development here in our numerical situation. And what we learned from that is the following. Here I plotted the heat flow per contact line length. So that's watt heat flow per length of or watt per square meter multiplied with the thickness of the contact line area. So it's watt per length of contact line. And we can see an interesting thing here. When the droplet impinges, it spreads. It has a positive contact line speed and a high velocity. It spreads very fast. Then, with time, this contact line speed is slowed down until you have the maximum radius. And when you have the maximum radius, you have 0 contact line velocity, and then it changes velocity. It's a negative velocity, and then it slightly oscillates, and at the end, you have the sessile droplet again with 0 contact line velocity. So if I look at from a point of view of time, it starts here, the droplet impingement event, it goes here. Here's the point of return of contact line radius, then it goes here, it vibrates a little bit, and then it ends here. And we see a very interesting thing. So when the droplet spreads, we have an advancing contact line situation. In the advancing contact line situation, from the numerical results, we see that we have such a flow. So we bring cold fluid, subcooled fluid from the bulk of the droplet into the contact line area. And this presses, these colored lines here are the isotherms, constant temperature. This presses down the thermal boundary layer at the droplet here, base. This is the wall here, and this is the droplet. That means you have very high heat fluxes here, but you have no evaporation. So this goes into heating up the droplet into sessile heat. When the droplet removes in this situation here, you have a receding contact line speed, which is typically much lower, as you saw in the video before, than when it hits the wall here. But then you have an opposite flow. The opposite flow takes hot fluid from the boundary layer and moves it towards the interface. That means you get higher temperatures here at the interface, and that means you enhance evaporation because the interface gets hot. Here the interface is rather cool, low evaporation rate, and here high evaporation rate, high temperatures at the interface. So the learning outcome is the following. When you have a droplet impinging, there are 2 phases. First, an advancing contact line phase, spreading droplet. Here the energy of the heater goes mainly into heating up the fluid, temperature-wise in the liquid phase of the droplet, and partly, of course, some evaporation, and partly some pure convection directly from the heater to the gas phase due to natural convection, and a small part of direct evaporation, not from the bulk of the liquid droplet, but directly near the contact line. And this situation is, of course, the same when the droplet recedes, but the amount changes much more. Then the droplet has almost a constant temperature, but it's due to the receding contact line situation, this energy is in a mean sense, the energy of the droplet does not change too much, but the hot near wall temperature is brought to the interface, and therefore the evaporation is much higher in this situation than in this situation. Now I come to the numerical simulation of basically with the same method for boiling. So here you see a nucleate boiling of a single bubble, at a superheated wall. We start, of course, the nucleation artificially in our experiment, in our numerical situation, in our numerical program. And we compare this experiments now again with simulation. This here is again slow motion. And what we see with our different measurement techniques and then with the numerics is the following. For example, we place here this transparency that I show you, this slide, we place our micro-thermocouple just above the artificial nucleation site in the experiment. The micro-thermocouple was developed together with my colleague Hein Auracher from University of Berlin. It has only a tip size of 13 micrometer, so a very high measurement frequency. And we see, for example, this here is HFE 7100 at 500 millibars, so a saturation temperature of 40 degrees C. And you see that here, when the tip of the micro-thermocouple is above the vapor bubble in the boundary, in the hot boundary layer, it's only slightly subcooled here, the liquid pool. Then we have a very high temperature, about 7 Kelvin superheat we measure here at the tip size compared to saturation temperature. When the tip of the micro-thermocouple is inside the vapor bubble, we measure saturation temperature, and here and there. And now it comes out of the rising bubble. And then when the bubble detaches, a cold liquid is brought from the pool into the thermal boundary layer, into the wake of the bubble. So this here now, cold liquid has flown here, and now we see a slowly rise of this temperature. So first it's cold liquid. This cold liquid, due to the hot wall, heats up again until it reaches high enough temperature for the next nucleation. This is also what we see with our two cameras in the boiling event. So here the temperature profile and here the heat flux profile. And if I plot the temperature and heat flux along this dotted line here, I see the following. When the bubble is initiated now, it's strongly cooling here, strong delta T near the nucleation site and the surrounding. Then we have a minimum ring-shaped temperature area, cooling area here near the contact line, specifically very strong cooling when it goes from the growing phase into the detaching phase. And just qualitatively in the opposite direction, we have a maximum of evaporation rate or maximum of cooling rate, heat flux here in this ring-shaped area. Again, if I plot here in this, of course, I have to define, let's say, the contact line influenced area, and we define it just by giving it a certain size between these two lines. Here's the contact line, and we integrate between these two lines. And if we take this integrated heat flux, we see this here is the contact line evaporation. This is the latent heat flow in total. And this here is the evaporation and also condensation at the bubble hull here. And of course, if you add this and this gives the total latent heat flow. And you see that in the adsorbed film area, we have only very little heat transfer due to natural convection. And also the transient conduction here around the bubble in the fluid is rather low compared to the latent heat in this situation. But here in this situation, it's also saturated, basically saturated fluid, so no subcooling. Of course, this depends very much on subcooling. This is just an example. What we learn is the following, that we have a maximum heat flux here near the contact line. If I plot the heat flux versus the radial coordinate, and here this is a half of a bubble, and this is the thermal boundary layer, we have a maximum of heat transfer here in this area. And we can see that this heat flux maximum, of course, when the bubble is growing, travels radially outside with a contact line. And when the bubble starts to detach, we change the contact line velocity from a receding situation to an advancing situation, from this situation to this situation. And then the heat flux maximum is even a little bit higher. And as it increases with the contact line speed, also the maximum here slightly increases because the speed of the contact line is increasing. And again, we can look into our numerical model and see what happens in detail near the contact line. We see if we have a bubble growth, that means the contact line is a receding contact line. It travels in this direction, vapor here, liquid there. Then we bring hot fluid from the boundary layer in the liquid phase towards the interface. So we increase evaporation here. We have very high temperature gradients next to the interface, so strong evaporation here. While when the bubble detaches, we have the opposite direction of the contact line, and then we bring cold fluid here into this area, and we have such a flow, partly evaporating here, but the rest goes into the boundary layer here. That means the isotherms here, the temperature gradient is not as strong, so here we have slightly lower evaporation than in this case. Now, what did we learn? And I come to the conclusions of my talk. We learned that this contact line, moving three-phase contact line, has somehow a rather strong influence on such situations of drop impingement cooling and boiling heat transfer. And the contact line, basically the events or the phenomena in the contact line are the same, independent whether it's in this macroscopic situation or it's in this macroscopic situation. So the local evaporation in the tiny three-phase contact line region is a major heat and fluid transport mechanism in both situations. We saw that the three-phase contact line heat flux is different during the wetting phase with advancing contact line here shown for the droplet, but the same for the boiling event and the de-wetting phase and the receding phase. We see that in the wetting phase, cold bulk fluid flows into the hot boundary layer like this, while in the de-wetting phase, hot liquid from the boundary layer flows into the bulk in this direction. That means that here in this wetting situation, the heat flux per unit contact line rises with contact line velocity, while here it's almost independent from the contact line velocity we found out. And it also means that here sensible heat transfer is rather high, because the high temperature gradients are here, far away from the interface. Latent heat transfer is rather low here. And here it's just the opposite. Sensible heat transfer is rather low. Temperature gradients at the interface are much higher, therefore latent heat transfer is higher. Some small outlook. From a general point of view, our next aims is to bring all these studies together into a comprehensive study, and we try to find some correlations based, of course, on dimensionless numbers like the Reynolds number, the Weber number, and the Bond number, because that's what we would like to do, to bring it into a textbook as a correlation. But I think this is quite a step to go still, so this won't be ready next year, maybe in 2, hopefully maybe also in 5 years. Another thing we want to study drop impingement at higher Weber numbers, because at very high Weber numbers you have splashing. We are not able to simulate splashing. We started some preliminary calculations with higher Weber numbers where we can see some instabilities. Of course, these instabilities force first fingering, and then at even higher Weber numbers, splashing of droplets, so you get secondary droplets. But this is very difficult to compute, and we are even not sure if this is, let's say, at high Weber numbers due to the high forces that you have here, inertia forces, if this is more a numerical instability or real instability. We don't know, but we will go on with these studies. We also do some drop impingement experiments for temperatures above Leidenfrost. So here's the wall. The wall is above Leidenfrost. That means when the droplet is coming close with a low velocity, very close to the wall, evaporation takes place here before it wets the wall. And so you have a vapor cushion here, and the droplet does not wet the wall. I would dream to see also the transition from above Leidenfrost to below Leidenfrost in a numerical study, but we are far away from that. It's just a very beginning. And what we did, because our center is called Smart Interface, we wanted to build a smart interface. We had a colleague from the US, I²CNER, in our lab for quite some time. I²CNER named here in this presentation also. And we did investigation of drop impingement cooling above Leidenfrost temperature. So we first took a bare steel surface. If a water droplet is hitting, it's just splashed above Leidenfrost, almost no cooling, so temperature does not change a lot, no cooling effect above Leidenfrost. And with the help of Alex Yavin, he developed a method to produce some nanofibers with black carbon nanoparticles inside and cover the steel with that. And when the droplet hits this type of steel covered with the nanofibers, it penetrates into the nanostructure, it wets the nanostructure, and it does not splash. Yeah. So even though the initial temperature is basically the same, it penetrates the wall, you have strong evaporation from the wall, and even though the initial temperature is above Leidenfrost, we can cool the wall with this kind of smart interface. So that's a preliminary result with a smart interface for cooling techniques. And, very close to the end, we start now also to compute bubble mergers, not only a single bubble, but only multiple bubbles, because we want step by step go to closer bubbles that interact with each other, and my dream is to go further on close to critical heat flux. What you can see here also is quite interesting. Here I show the temperature, and here I show at the wall surface, I show the adaptive grid size refinement, because that's very important that we have adaptive grid size refinement. And what was also quite interesting for us to see in this numerical, when these two bubbles merge, they leave a droplet here in the middle. And we found this by occasion, also in an experiment, only by occasion, because occasionally two neighboring sites were activated at the same time. This is not very often. Most of the time one is activated earlier as the other, and you don't see that. In the numerical event you can see that, but once we had it in an experiment and we saw also the sitting droplet. I want to acknowledge, first of all, for the fellowship that I have here in Japan, and that makes my stay very pleasant here in Japan, from the Japan Society for the Promotion of Science, JSPS, for their really generous grant to stay here in Japan for a couple of weeks. I want to thank very much my sincere host, Professor I²CNER, for his kind support and for his perfect organization of my visit. And of course, I want to thank my PhD students doing the numerical work and experimental work that I presented here. Domo arigato gozaimasu.